In this last video in section 11.2, we're going to look at question number 8. And just to paraphrase this one, this problem deals with Galileo's experiments on freely falling objects. Let's say, for example, I drop a bowling ball off the side of a cliff here. Okay. Now, Aristotle, 1900 years prior to Galileo, said that heavier objects fall faster than lighter objects. So for example, if I dropped a golf ball off the same cliff at the same time, according to Aristotle, the bowling ball would hit the ground sooner than the golf ball because, well, the bowling ball is heavier. Okay. Well, what Galileo found was that, well, if you ignore air resistance, it turns out that the two objects are actually going to fall at the same rate and hit the ground at exactly the same time. And this has to do with the acceleration due to the gravitational force. However, it turns out also that it's hard to analyze, back in Galileo's day at least, right, this kind of motion given the tools that were available at the time, right? I mean, Galileo dates to basically the 16th century here, right? So he had this ingenious idea to observe, say, a ball rolling down an inclined plane. This gave him a much clearer look. It slowed things down, but the key observation, using some arguments from physics, you can show that the acceleration of the thing going down the plane is actually going to be the same as if it was just freely falling. So this is the big aha moment. Okay, so over here we have a table of data, right, with some various times and distances fallen from an object that's been dropped off the side of a cliff. And our job here at the very bottom, it says, is this linear or quadratic variation? And so let's go ahead and take this data and first assess, is it going to be, say, linear? All right. Now we can do that pretty simply by just looking at the ratio of the distance to just the time. So for this first pair, I'm looking at the ratio of 4.9 to 1.0, and that is a ratio of 4.9. But now for the second pair, I get 11.0 divided by 1.5. Well, that's not 4.9. It's something like 7.3 repeated. So that alone already allows me to say, right, this is not direct variation in a linear sense. Okay, so not linear. All right, so let's go ahead now and look at, say, the square of the time. So like we've done in some of these other problems, I'm going to go ahead and put in a little extra column here with the squares of the times. So this would be still 1.0. 1.5 squared is 2.25. 2.0 squared would be our 4.0. Then we're going to get 6.25. Then we're going to get our 9.0. Okay, great. So now let's go ahead and look at the ratio of d to t squared. And if we do that, what we're going to find there is, well, 4.9 divided by 1.0 is still 4.9. But now if I do 11.0 divided by the 2.25, you can check that that's still 4.9. And likewise with the next pair, 19.6 divided by 4 is 4.9. The next one here, 30.6 divided by 6.25, that's still 4.9. And then lastly, 44.1 divided by 9.0, well, that's still 4.9. Okay, so that's telling us here that the distance divided by the square of the travel time is equal to 4.9. Or put another way, the distance is equal to 4.9 times the square of the time. So here we in fact have quadratic variation. Okay, and it turns out that the constant due to gravitation, this is a special constant in physics known as G, that I make this comment here down below. Turns out that that 4.9 is half of that special constant. This constant here is about 9.8 there, okay? Well, that's a good place to stop, and I'll see you in the next section.